southeast or whatever. Southeast.
You got this.
I don't think that the peach voting sticker counts if it's the New York mail race. Exactly. I don't think that counts.
Early voting ends tomorrow, November 4th, Atlanta City Council and public commission.
Really good, really good.
That's my outfit is liberal.
Oh, that's why I was like, where's Todd?
I don't believe you.
Next year, all of us with Star Trek.
With what?
Next year, all of us with Star Trek like systems.
I get a blue one.
Yeah.
Not wearing red. Who's gonna wear the red shirt though?
Actually, I was thinking a man in yellow, me, Team Mason, Karina in red, and then Todd in blue. If a man is not here next year, it will change. Hopefully, he will not be here, right? So, hopefully.
Or do you all have to be red because of your small stars? You all gotta be red.
Yeah, but they have different meanings, the colors.
Oh, yes.
General culture.
I'm sorry. My wife calls me an uncultured swine. I think that it's been established. So did Rachel. Lots of people have called me that.
No, you're fine. Can you ask to turn off the lamp lights?
He's busy. I'm gonna wait for him to.
Okay. Or you can serve and you can.
Yeah. Hello, everybody. Welcome to Astronomy on Tap. It is our 2-year anniversary. Thank you all for coming out tonight. J-Rob had one too many, so I'm hosting. Tonight we're going to have a talk about Spooky Worlds by Captain Sebastián Gaxiola. Close enough.
Yeah.
I'm sorry.
Yeah.
I met Sebas when I was applying to grad school. We both were waitlisted at New Mexico State University, and I was annoyed because he was better at speaking than I am. I guess joke's on him, we've ended up at the same place.
Mm-hmm.
But it's going to be a real treat. Sebas specializes in cave dwarfs and studying their features and things in the solar neighborhood, trying to identify where's the best place to find life. But before that, a quick announcement. We have a member from the Charlie Elliott Astronomy Club, Joe, here tonight. And we want to advertise for them that they have a Charlie Elliott Dark Skies Observing Night on November 15th out at the Charlie Elliott Wildlife Center, which is an hour and 15 minutes west near Madison off of I-20. I don't own a car, so that's why I'm confused. Oh, right. And we have a QR code on the bar if you want to learn more about Charlie Elliott Astronomy. They're awesome. They have a lot of amateur astronomers who show up with really big telescopes. And it's a blast to go see them. I gave a talk to them like a year ago. They're all really kind people, and they're all really good at pointing telescopes at things. With that being said, I'm gonna hand it off to Captain.
Thank you, sir.
Yeah, that's it.
Well, hi everyone. My name is Sebastián, Sebas for short, and I'm a astronomy PhD candidate at Georgia State University. And I want to talk with you about spooky worlds and how we found them. Okay, but first I want to do a Halloween costume check. If this works, hopefully. No. Okay. Um. Yes. So raise your hand. Who has a Halloween costume right now? Okay. For some statistics. Okay. 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 Good. The deer here with alopecia has a Halloween costume too. Perfect. So, just a little for warming up, I want to tell you what my previous costume ideas. Some of you already know, okay? My first idea was a xenoform, right? They sell the costume, it's really cool. I will do once, maybe next year. Venmo me, it's expensive. Also because I saw this TikTok a few years ago. So I want to. It's a xenoform in Mexico. Like I can recreate this. I know how to dance like that. So that's fun. And my other idea was Tecal the hat. So I will do it again. That's my plans. But someone in this place told me that either those costumes have a mask and a tail. It won't be good for like presenting in the public. And that personally, a tail will be too distracting for them. So like I don't want to ask more questions. Okay, I don't know. I don't want to know why. But yeah. So now let's start with the science. So a little about myself. I'm from the northwest of Mexico, where baseball is more popular than soccer. Okay, where one of like typical foods is actually sushi. We have more sushi places in my city than taco places or anything else. That's weird, you know. There's a map with all the Pacific League teams. So I'm like from here, from Tomateros, like the tomatoes people, kind of. Also, we have a team from Tucson. You started into our league, and so I did undergrad in this city here, and it's where I started doing research. I started doing galaxy research actually, like looking at galaxies for like taking images of galaxies with this telescope in the north of Mexico here. This telescope is really cool. They have a lot of science with cosmology, galaxy, etc. But then I moved to Mexico City and doing exoplanet research. Okay, using different robotic telescopes in the San Pedro Martir Sierra Observatory here. Oh, sorry, here in around this part in Mexico. Really beautiful place. And then I moved here to Atlanta to make research on stars using telescopes in Chile. So I've been a couple times to Chile. This is me, my advisor, my really good friend Emma, in the telescopes, and it's been just a blast since then. Okay, so now going forward to this talk, it's about worlds, not planets. I mean, it's about planets really the talk, but when you think about a planet, it's really narrow in the definition, so you can think better of them like if we call it about worlds. And even our solar system has different types of worlds, including the planets here, right? We have this is scale of sizes, not distances. Okay, so you have the Sun, Venus, Mercury, the Earth, right, and Mars, Jupiter, Saturn, Uranus, Neptune, right? And you see all the moons here, the bigger ones. Also, more worlds. We have all these different solar system moons with Mars as comparison, and sometimes you have moons as big as Mars or bigger than the moon, our moon. Okay, so these are many bodies in the solar system, right? Many worlds. I mean, maybe one day we'll explore, hopefully. But also we need to think about if we see this many stars in the sky, like trillions of stars, we don't know the number exactly, neither of our galaxy. We think we underestimate the number of stars in our galaxy because we cannot see the smaller stars, like our group will say, right, or statistics. And we can think of maybe every star probably has at least one planet. And if you have at least one planet, I mean, you have also dozens and dozens of moons, right, per system. So, but how we study stars? So I'll tell you that we use a light, cameras, and then we can study stars. So in this video, I'm going to show you animation from observing the Omega cluster, the Omega Centauri cluster. It's in Hubble, and it's really good at telling how we study stars. Like this will be our first point of study. Okay, then you can go and add more layers, etc. But this is one of the first layers using the Hertzsprung-Russell diagram. So first, you see the field sky, right? The patch in the sky, deep sky. You see all the stars. You see different colors from red, blue, white-ish. Then what you can do is separate them between the hotter stars. And one side, the blue ones are the hotter, to the cool stars that are redder, okay? But still, you see different sizes, right? So then we can arrange them from the bigger and more luminous to the smaller and less luminous stars. Okay, you see the structure now from this specific cluster. Then here we can see different areas. The main sequence stars, these stars burn hydrogen. Okay, then we see evolved stars, the red giants. These stars were here, then they evolved and they went all the way here. Then we have another part of evolved stars, the blue red giant, and then the white dwarfs. This is where the stellar cores or solar-like stars are. Okay, so let's go back to the Hertzsprung-Russell diagram. Again, the bigger the star is in this axis, and the cooler the star is in this axis in this part. Okay, and we see different types of stars, like we see the blue giant, supergiant stars, the sun-like stars, the red dwarf stars, and here the white dwarfs. So here we have, so this diagram tells us about the evolution of stars. First we see them, and then we can start studying their evolution over time. Okay, so here we have different stars again. Here's the more massive stars in this direction, and then over time. So we see that for blue giants stars, they eventually will go to supernova, and then, depending on the mass, they will go either to a black hole or they will end as a neutron star. Okay, then stars like our sun, they will become red giants, and then in their lives they will be white dwarfs. Okay, I mean planetary nebula, then white dwarfs. And for red dwarf stars, they will go fully from red dwarfs, then they will cool over time. They will never be in these two phases, and then eventually will become white dwarfs. Okay, but also the massive the star, the more rapidly will evolve. Okay, so the time scale between these is 10 to 100 million years, when these stars will take trillions of years to evolve. Okay, so I'm going to explain you in this talk worlds we discover in this type of stars here. Okay, around neutron stars, around sun-like stars, red dwarf stars, and white dwarfs. Okay, so first we'll go to the first detection of exoplanet ever. Okay, in 1992, it was discovered a system around a neutron star that we call millisecond pulsar. It means it pulses every millisecond. Okay, and these stars, these objects are the size of a city. Okay, so these are the end of the lives of stars with dozens of solar masses, and at the end they will collapse over themselves and they will become an object of like 10 miles. Okay, I mean plus minus too much. I don't know. I mean they always have different numbers. And if you take a spoon of material of this star, it will weigh as much as literally a moon. Okay, like a small moon from Jupiter. So in this system, actually we found 3 planets. Okay, so in this graph here, you have the comparison of the sun and some of the planets in the solar system, and then the pulsar star PSB B12, this number plate, with 3 other planets. Okay, really close to the actual star. And this star has also huge radiation jets from itself because they're spinning really fast, and then the magnetic fields are misaligned, and you need to know that they have huge jets spinning from here, and maybe those jets actually interact with the atmospheres, if any, of the planets. So you can see an aurora here in this example. It's artistic representation. But we said, like, how we detect these worlds? So we use the Arecibo Observatory in Puerto Rico. It's not working right now. I mean, it's a whole story. We're really sad. But the thing you need to know is that the star is spinning really fast, and every time a beam like points to us, we'll see a beam, a peak. Okay, so we can study the periodicity of the beams of this pulsar, and then we can apply something called the Doppler effect. Okay, so the Doppler effect means if you have any signal or like sound, okay, you will hear a siren going like from, let's say you stand up and you see a siren ambulance, right, and going towards you and then away from you, and then the waves, what will happen with the waves are that some of the waves, where do you see this? Some of the waves as the star is moving, they will go bluer. That means it's going towards you, and then they will be observed as red if they're going away from you. This is called blue shift and red shift. Okay, this is waves of light. In radio, radio is another source of light. Okay, like visible light, like X-rays, like ultraviolet. And we see how this pulse can go back and forward. So if this pulse goes back and forward over time, empirically, we can say something else is perturbing the object. Does that make sense? And then you can see more perturbations in the same signal saying, okay, this is only one object, it's multiple objects. And then you can get what type of objects will make this perturbation, and you can say, okay, something close to an Earth-sized object mass. So actually NASA a few years ago made a whole thing called Galaxy of Horrors, making posters like this about the system, like they said they were spooky systems, okay? Because literally these are zombie worlds. They survived the supernova explosion of their host star, okay? So we don't know what happened with the planets. We will never know. Probably there were no aliens because these stars survive real short amounts of time. And if they were aliens, maybe they flee from the star, hopefully. Okay. So next planetary system, we want to talk about 51 Pegasi. This was the first exoplanet found around a sun-like star, very similar to like the sun. So if you see the star, the comparison of the star, the 51 Pegasi to our sun, it's a little bigger, a little more massive, a little hotter than the sun. And the planet is also a little bigger and more massive than our own Jupiter. Okay, this discovery led to the 2019 Nobel Prize in Physics for the first detection of a planet around a sun-like star. I remember this time, it felt like holidays. It felt like all the media was about exoplanets, all the media was about the free discovery. I was already doing research on planets around this time. My advisor was getting like called every day to like do press releases back in Mexico. I was really grateful to work in a project with him too, with Didier Kellos. So I had meetings with him in Zoom. Like, the hell, I took screenshots and everything, and like I showed my mom. I mean, it was a big thing when you were undergrad. I mean, still. So how we detect this exoplanet? They used a telescope in France, in the, who knows French? I can pronounce this correctly. Not me. Nice. Good. I will put the like little like how you pronounce it here next time. So, oh right, yeah right, like Portuguese. Anyways, so they use a method called radial velocities, or they saw the stellar wobble. Okay, and how they do it is they use a spectra, and the spectra means if you have the light, the white light for a star or any type of light, and you diffract the light with a prism, you get the rainbow, okay? And the rainbow actually can tell you if the light from the star, the light gets absorbed by the atmosphere of the star, and then you will see different lines, like dims here, that they will tell you different elements that are in the stellar atmosphere. They can be elements like calcium, like hydrogen, iron, lithium, magnesium, sodium, etc. I do this for a living. Okay, so I've seen many spectra, many type of my stars. I had dimers, also spectra. But then you can see this. This animation. You'll see how we see the spectrum of a star with the dark lines, and as the planet wobbles, we don't see the planet. We see only the star. Okay, so we can see how the spectrum goes back and forward, and the difference between the line shift is the velocity. And then from these velocities, we can say that, okay, there's something going this fast on the star, you should have these characteristics. And I don't work really much with this type of stuff. My friend Tim here, Tim, say hi. He does this for like 1,000 stars, okay? So he's viewing data. You want to help? We appreciate that. So a few things interesting about this system is that this system is only one hot Jupiter. We call hot Jupiter because it's orbiting really close to its host star. Okay, that close as only almost 8 million kilometers, or like for this whatever a mile is, 4.6 million miles. When AU, the distance between the sun, very central, like the center of the sun, in the Earth, is around 150 million kilometers, or 93 million miles. So this system is really close to its star. Okay, it's like a Jupiter-sized planet, so close to the star. So when we found this, not me, I wasn't even alive, but we as astronomers, right? We're like, no, it shouldn't be this, right? It should be another, because we found stars before, like with this method, but not real planets, because they're kind of, the ratio between the star and the planet is so little, so it's hard to detect. Okay, so this literally define or understanding of close or planets orbits. We thought only a small planet should be around their stars, because maybe bigger planets will work like the sun, right? You have Jupiter like 20 miles, 20 AUs away from the sun. Also, this system is tidally locked. It means it's only showing one face of the planet, the star, like the moon does with the Earth. That's why we only see one part of the moon every night. Okay. Also, it also means that we have extreme atmospheres in the universe, right? Actually, the atmospheres of this set of planets are even like rocks. Okay, you have iron clouds, you have metal clouds, and it rains also like metals. This discovery between the first exoplanet and this one, it made a new field in astronomy that is even like 30 years old now. When you have fields like cosmology or fields that have hundreds of years, like 100, right? Not hundreds. And also this led us with open questions about formation theories. we didn't know how these planets form. So we started looking for more planets. We started to design more missions to design, to send to space or make more projects here on Earth to find more planets like this or any other type of planet, okay? But first, we need to start with stars, okay? So, next, as our third world, we have TRAPPIST-1. This is a multi-Earth-sized planetary system around an ultra-cool dwarf star. They were found also around was an undergrad, 2017. And this star is as small as Jupiter, but has 7 Earth-like planets, Earth-sized planets, okay? So for example, in this animation, you can see how you start in the middle, and all these planets are orbiting this star in periods of days, not even months or years, it's just days, okay? So we detect this planet with the TRAPPIST telescope. This is the acronym for Transiting Planets and Planetary Small Telescope. This is a telescope in Chile, actually. And it's a collaboration between the European Space Agency and schools in Chile. And actually the name is because a type of beer. Can you show it?
Yep.
Yeah. The Trappist beer is really popular in Europe. And they are made by monks. Okay?
So good.
Yeah,
So good.
very fitting, right, to this environment?
Yep.
Yes. So we need to make a telescope, like 3 taverns telescope, I don't know. 3T. You want to fund that, right? And what detection method we use? We use the transit detection method. That means we see starlight, and when a planet pass across, eclipses the star, we see a dim of light. Okay? So from this dim of light, if we see periodically, like every day, 2 days, etc., we can say, okay, the planet is orbiting the star every 2 days, 2.5 days, etc. And we can also get parameters like the radius of the star, the planet, etc. It's not as easy, really, but it works, and something you can prove with different telescopes around the world, and anyone can make their own results or assumptions of this. So, for example, they not only use space ground-based telescopes, they also use space telescopes. So TRAPPIST, how it works, is a net of telescopes around the world, and they use blinding observing stars. And the moment they see one, they will say, "Oh, I think we found one." We're gonna ask more people to observe the same object to see if what we see is real or with better instruments. And then you can go to space. I mean, you write a proposal, really stressful, even for the space telescopes, and say, like, okay, I want this many hours with this telescope to observe the system. And they did that with Spitzer. That's a telescope observing the infrared. Why infrared? Because the star is so small and cool and red. You need telescopes that observe more in the red than in the white yellowish part of the spectrum. So you can see this animation here, right? You see how different planets do the different dims, right? And they say like, okay, it's not only 2 or 3 planets. I think first they discovered 3 planets. Then when we went to space using this Spitzer, they found 7. And the sizes of these planets were kind of the size of the Earth. So how a star as small as Jupiter can have 7 planets? Okay, it just defy all our understanding of stellar formation. Okay, so a little more about this system is you have the sun that is way bigger than the star, but also the star is almost the same size as Jupiter. It's a little bigger, okay, but it's not quite the same mass. It's hundreds of times the mass of Jupiter. Then we think that the planets around TRAPPIST-1 are a little bigger than the inner planets in the solar system. Why do you say that we think? Because I mean, at the end you also do a lot of guesses, assumptions, right? So the true size we don't know. We have the best guesses with our technology and etc. On our models. I'm gonna go back because you see here how Jupiter also has the Galilean moons. They are really way smaller than the planets in their solar system or the planets from TRAPPIST-1. But if we compare orbits, for example, let's go first to the bottom plot here. You see the orbits of the inner planet solar system here, okay? Then a little zoom in, you will see in red the orbits of the planets on TRAPPIST-1 system. And even smaller than this are the orbits of the Galilean moons. So this is just a game of scales, okay? So the closest example to this system is Jupiter and their moons, okay? We cannot compare our solar system really to what's happening in this system. So the NASA has a lot of different type websites, animations, and you all should just go and dive in it because you're paying taxes for it, right? And they have this website that it's like if you were on the surface of one of the planets in the 4-planet TRAPPIST-1D, and this is how you will look the sky from one of the planets. Okay, that's my cursor, and you can see like all the planets around here, right? This is not sci-fi. I mean, I always say like, even I think George Lucas actually he thought of planets and systems way before we discovered them. But also, there's no planet like I think in the like normal mainstream media that is weirder than the planets we found. So you see any planet in a TV show, movie, etc., there is a way weirder planet in our archive of exoplanets. That's take a word for it. Then our fourth system will be the system around a white dwarf or stellar core. So this was the first exoplanet that we discovered around a white dwarf, the end of the life of the star like the sun. And they was discovered in 2020. Actually, I was writing my senior undergrad thesis when I was doing this, and actually related to this field. Like I want to show you in a few moments. So these cores are actually the size like the Earth. So the star just evolves, then I want to explain what happens after that. And when you have only the core, there's just compressed material. Compact material, they are just the size as the Earth. The more massive the star, the smaller it will be. Okay. So for example, in these examples, Sirius B, it will be more massive than Procyon and the how do you pronounce this? Van Manin star. Okay. So these are just for comparison. Okay. But how do these systems get to exist? So you have a star like the sun, it starts evolving, then it spins by process I won't explain here because that's another talk, and now I'm not gonna do the talk. But then you have the atmospheres going there, they detach from the actual core of the star, and they will cool over time. So you will look something like this. You will see what happened in a planetary nebula. It will expand, okay, over like thousands of years, not even millions of years. I think the scale is like 10 to 25,000 years. And then you get only the remaining thing, the white dwarf, okay? The question is, what happened with the planets around them, okay? So we've been asking this question for like many decades now. And then you can see all these examples of planetary nebulas just waiting to be cool and fade away in space, okay? So we have many examples. My personal favorite is the Schemo Nebula, NGC 2392. Nice, yes. They're all pretty. The different colors mean different elements, okay? Also, they have weird shapes because something happened when they started to expand and evolve. Some of them, their shapes are because they had companions, other stars shaping the environment there. So the whole shape of the system, it will be because something else is having a gravitational pull in the star. So for many decades, we've been thinking like, what happened to the planets around solar-like stars when the stars evolve? Okay. So one thing, like, you can take the spectrum of these little stars, the white dwarfs, and normally they should be only elements like hydrogen and carbon, use the stellar cores. But sometimes they show weird things. This is the same, like this scale, this little rainbow spectrum with this plot. The y-axis is just the energy, or how much energy or light is in that part of the color. But these stars, I don't think you can see it here, but sometimes you have magnesium, sodium, lithium, potassium, etc. And if you recall, maybe not, I mean, maybe because I'm just on Earth, these elements are what are rocks made of, silicates, okay? So why are we seeing silicates and rock materials around the stellar cores, okay? We call them polluted white dwarfs, stuff that it shouldn't be there. And one explanation is that they can have, and we found this actually, they have just disc material, and also some of the material is accreting into the white dwarf. Okay, so we've seen just white dwarf ripping apart planetary systems and getting accreted into the atmosphere of the white dwarf. Okay, also really weird is like we found material like ratios with the combination of elements that are not even in our solar system, because you can do many combinations of material elements. You can have like different species, right? But we found ratios like mixing of materials in these systems that are not in our solar system. So they have new type of rocks. Okay, so the weird thing with this system on the white dwarf is that we found a Jupiter-sized planet, not a rocky planet. Okay, so how a planet will survive, like a Jupiter-sized planet will survive a star like this? So we detect this planet using the TESS space telescope for test for transits of planets through satellite, using again transits, and this is animation of how we detect this system. You see the planet, you see the little star around the size of Earth, kind of. It's a little yellow because it's a little cool. It's not white as the name. You can ask me that later. So we see this planet in an orbit of, I think, like 20 something days. Hopefully, maybe not lying, maybe 7 days. Again, we see the transit of the star eclipsing. Then we went and used Spitzer again to observe this system, and we found more precise transits. What happened here? Oh, yes. So you have the star. At some point, it will evolve. It will planetary nebula, and you have the remaining planet here. So we're still trying to find out how is the migration mechanism between the normal orbit to where the planet is right now. Okay, we don't know yet. Also, it's a triple system, so there are two stars really far away from this. I don't think that makes any like influence on this. So again, let's go to the system parameters. The star is way more smaller than the sun. Okay, it's like comparing the sun with the Earth. So here you have the in this part the orbit distances. You have the sun, you have Mercury, Venus, Earth, Mars. Then here you have the white dwarf, and really, really close, technically, the Jupiter-sized planet. And you go and compare the sizes, you will see the sun like really big, then 1% of the sun, around 1% will be the size of the Earth. Then you will see here the white dwarf, almost the same size of the Earth, and the huge planet. Okay, actually, the transits of the system, the planet just blocked the 100% of light of the star, because the star is so small and the planet is relatively big to it. So they use, at some point you see like you have a star, and then next thing you don't have a star, right? It disappeared, and then again you see the star. So, how much is it? Good, I'm time. So, I'm gonna circle back to earlier. Costumes, maybe. I mean, I'm kind of done with this costume. The waist too tight. So, like, you want to work at Starfleet, you need like a tiny waist.
Maybe the Patrick Stewart, like the pull down.
Yeah. I don't know how they do it. Like, Captain Kirk, fit, skinny. Anyways, I'm not holding my breath. I'm fine. So earlier I told you that I study K-dwarf stars, that they're the orange stars. This means the telescope in Chile. Telescopes also are really big. Okay. So for example, if you grab a piece of sky and you count like 100 stars in your hand, you will see that 75% of them are the little red dwarf stars. Okay. Then the second more abundant type of stars are the K-dwarfs, 11%. Then you see for every 100 stars, you have only 5 stars like the sun. So for every star like the sun, you have 2 orange K-dwarfs. Okay. This plot, also made by my advisor here. Say hi, Todd. Say hi to Todd. So then what I do is study which of these stars are the most habitable stars, and also like the young ones. We like the young stars because if you find a young star and then you find planets around a young star, you can say also the planets are young. Okay, if you say the planets are young, we want to use them as example of evolution of planets. So for example, this animation of my sample of stars. Here's the sun, and the whole cube here is around like 40 parsecs, or like 130 light years away. So I'm trying to look at them, like which ones are the best ones to look for exoplanets. Okay, and this is the part that I did in grad school. But in undergrad, I use telescopes in the San Pedro Martyr Observatory in the San Pedro Martyr Sierra in Mexico. Like this is San Diego and Tijuana. This is Mexicali here, and it's a really good place to observe because it's really it has a really good sky. You don't see many light here, like many street lights, etc. And my work there was studying all the telescopes there, and then see which ones we can use to observe transits. Okay, so I worked with 4 of them. They look like Star Wars canyons, but no. With Dottie, this telescope was meant to observe a huge field of sky, and then to find neutron star mergers or like gamma ray burst. So like, okay, we have data already from like different nights, and also the same field, the size of like 100 moons, you have 1 to 3 Jupiter-sized planets. So I was like, okay, let's see if the data works enough, like well enough to find Jupiter planets, like 51 Pegasi. So I didn't, because the precision for this type of science, for the original type of science, is not enough to find transits. But done. Okay, check. Now. Then I work with this telescope, TAOS-2. It's Trans-Neptunian Automated Occultation Survey. And this telescope is meant to observe specific fields in the sky closer to the ecliptic, or closer to also to the asteroid field, to see occultations by objects farther from the orbit of Neptune. So we can say like, okay, we can do statistics of how many Kuiper belt objects are in solar system. Kuiper belt objects are objects that are outside, like further than the orbit of Neptune, even the orbit of Pluto. Okay, But if you have observations, you have the data, and they took like 20 images per second, okay? Technically, you can use these observations to find planets around white dwarfs, because they're so tiny, and planets will go around really quickly, okay? So I was working with this telescope and this type of stars when, boom, they found the first exoplanet around a white dwarf. For me, it was like Christmas, because finally I had a paper to cite, calling a planet detection. Then later, I worked with Saint X. This telescope, Saint X, is also in name of Antoine Exupéry, the writer of The Little Prince. And this telescope is also part of the TRAPPIST network. They want to discover a TRAPPIST-1 system. So this telescope was meant to be, it's meant to be used to observe red stars to find planets around them. And just by luck, me studying the K-dwarf, me using this telescope, I got to observe a star called HD 110067, and I did observation of 2 planets around that star. I didn't know what I was observing. I just knew the instructions were a little weird because it was a K-dwarf instead of a little red star. So why is this happening? I was supposed to observe a star that bright or that orange. So we found a 6-planet system around this star, and they did a really good animation about this. It's working.
Yeah.
This started in 2020. Is there sound? No? Good. So we found the fifth exoplanet, right? Then we found these planets are the size bigger than the Earth, smaller than Neptune. Okay, their atmospheres are really thick as water. So they don't have the thickness of air; they have the thickness of water. And I observed the transits of planets E and F. I learned that months after. So that was cool because I had my notes, I had my stuff in my calendar, oh, I did this, right? That was really cool. But also, it was weird that it matches what I'm doing right now, certain K-dwarfs. Actually, this star is in our catalog of stars. I have a question for Tim later. And also, the thing of this planet is a resonance system. That means, so for every orbit, from the little star, the little planet in the first orbit, for every 2 orbits, the next star we have 1 orbit. Then the next star we have also a even number time of orbits. So this system is really what we call really stable. Okay. You hear the video with the sound. You can see little every time they cross the line of sight, it has a little sound. So at the end, it makes a song, because some of the music theory it tells you have resonance notes, it will sound like a song. So they make a song with this system. And when I was making these slides, I was like, wait, I've done a little bit of each spooky world research, right? So okay, I can put it in my slides because I never realized it until now, after 4 years. And one last thing, just to end, we Godspace are doing an exhibition at the Dia de Muertos, Day of the Dead event at Oakland Cemetery. So we have a little stand with telescopes, NASA swag, fun facts, etc. Also, they will have music, real Mexican food. Yeah, it will be great. There goes thousands of people. Every year is a blast. I chat with the people at Mexican consulate, and they give us a space. So I'm really excited, and I hope you can make it. This is this Sunday, November 2nd. So you can scan this QR code, and we'll be there. Well, thank you so much.
Thank you, Captain Sebas, for the talk. I'll get out of the way. Do folks have any questions? I'll run out to you. I got one to start us off.
Mm-hmm.
So you make a distinguish between planets versus worlds.
Mm-hmm.
Can you explain a little bit more, like what is a world, and then what would not be a world in our solar system?
First, what's a planet?
Debatable.
So maybe the broader word to name planets, right, would maybe a world. Because when you have moons that they look like planets, but they're not planets because they're orbiting a planet, right? Sometimes you have moons even bigger than planets. You have moons bigger than dwarf planets, right? It's a whole conversation. We have decades with this conversation. We have conferences just for this conversation, right? So I would say the world is just maybe somewhere you can land, maybe, right? You can land Jupiter, right?
Not with that attitude, though.
A lot of times they say 10 kilometers.
10 kilometers?
10 kilometers.
Okay. If you play Mario Galaxy, for example, I don't know if you know classic players, you can land in different like asteroids and planets.
Yeah.
Question?
Could you go to slide 30?
30.
Yeah, I should know, yeah. I could probably do it, yeah.
Mm-hmm. What's the question?
It has. Yeah. Okay. So okay, the names of these things.
Yeah.
We have naming schemes that are like Greek and Roman mythology for most of the planets and the moons, and then we just all of a sudden switch to Shakespeare names for Uranus's moons for some reason. We've got an asteroid named after Anne Frank for some reason. I'm 100% honest. What is Eskimo about that nebula? Does it have lots of water?
It's the face and it's got the fur hood thing.
Is that what it is?
Yeah. If you see it through a telescope.
I do need amateur astronomers. Okay.
If you see it through a telescope.
Okay.
I mean,
I'm not gonna lie, I did that click immediately.
better answer than mine. I would say because vibes. But
It's not that clear through the telescope with your eye.
Okay.
It's more like a
Fine. That's all.
I can tell J-Rob has become a faculty because that's a statement and not a question. Does anybody have a question?
Should it?
Yeah, tell us about 51 Atlas.
Come in.
Tell us about 51.
Atlas. 31 Atlas.
31 Atlas?
51 Aggie. 51.
Outside of the presentation stuff. Yeah.
So the comet, you mean?
The comet. The Great Blue
Wow. Actually, I've been asked of the comet like 6 times in the past 2 days by my family. I would say it's just an interstellar comet. Yes, we know it's interstellar because the orbit of it is really hyperbolic, and they're pretty common. But we didn't have the instrumentation to look at them like really like in a broad area, kind of. As we advance in technology, we'll find more of them. They're common due by statistics. I mean, people that do theory stuff, they say, okay, we'll find many a year with this type of instrumentation, and as the more advanced you go, you will find more. It's not a spacecraft, no. I wish it were a spacecraft, really. It's just having the same behavior as we expected, right? There are some people, some institutions saying it's a alien craft, right? It's a lot of like alarming news, right? Because I mean, good that you ask to professionals here, right? Instead of just sharing the news or asking your family. I mean, I got a text from family members saying like, yeah, we discussed this for 2 hours last night. I'm like, why you ask me? Right? And like every time we see an object like that, we'll use all our telescopes, space and ground space, to observe them. They are really lucky. They can get observing time, and that's really difficult. Yeah. Any other question?
I was just wondering what the most up-to-date number is for the number of discovered exoplanets. Is it? I thought it was like 6,000 something.
It's over 6,000 now. I mean, I got an email earlier, but you can subscribe to NASA Exoplanet Archive. They will send you the newsletters every week. They're pretty good. But yeah, over 6,000 so far. Yeah, I had actually a slide with the histogram, etc., but I decided not to put it. And any more question? I don't care. Spicy, no spicy questions. Boring, no boring. Oh, there.
You said K dwarf. What is? Can you explain what a K dwarf is compared to a regular dwarf?
Okay, so I can go. Okay.
What
So
slide do you need?
so K dwarfs, we have dwarf means they consume hydrogen. Okay, so we have stars really big, like the blue stars, the white big stars, then the orange stars like the sun. We call them dwarf because they're kind of small. I mean, not small, but they are not evolved. Okay, and they're fusing hydrogen, right?
They're not dying.
They're not dying, like he said. Yeah, they depending how you define dying. But K dwarfs are just like cooler stars of the sun. Okay, they have. I mean, the color show they're like orange to like dark orange colors, right? The name should be in alphabetical order, but at some point, I mean, one of the like biggest astronomers in the last century, they were the ones classifying stars by the spectrums, and then they moved the system to not including some of the other letters spectrum, right? So this is just, I mean, at some point we will call it just, oh yeah, red dwarf, orange dwarf, yellow dwarfs, but this is more like for historical reasons, because then you have K giants, and the K giants are giant stars, I mean already evolved, but also yellow color.
They're almost dead too.
Almost dead too, yes. Very spooky.
Even though we haven't defined what's living and what's dead.
Yes. Any other question? One more? There.
How many of the stars in your sample have exoplanets around them?
Good question. 102. From 2194, 102 have exoplanets, and 518 have another stellar companion.
Oh, no, this one.
You were talking about the system that you found with the 6 planets, and you said their atmosphere was like water.
Mhm.
Is that sort of like when the Earth had the primordial ooze before it really? So they're kind of at that phase, sort of like the Earth, so they could possibly turn into an Earth, maybe.
Good question. Really great question, actually. And we don't know much yet about sub-Neptunes because we still think maybe it can be they form like that, right? And they have their atmosphere, they're just dense, right? It's like you've seen those videos when they go to lakes and then you see like everything clear and then like really like you see clear water and they have another layer of water more, right? It's almost the same in these cases. One of the theories that they form as like Jupiter's planets, and at some point in evolution they lose the atmospheres, so you only get the core and the remaining stuff closer to the actual planet core. But maybe you want to think about like aliens around those planets. They might be looking like whales, or like they're like things we see in the sea, right? But yeah, that's still be to known. Yeah, really great question.
I got one last one. What's the weirdest alien you've ever met in your travels around space?
The weird what?
The weirdest alien you've ever met in your travels around space.
The weirdest alien. My advisor is an alien, yeah, but not weird. Who? I mean, I like them all.
All right. All right, let's all give Sebas one last round of applause. spooky words that exist. Reminder to